Well, hello, everybody. Good morning, afternoon, good evening, wherever you may be, somewhere in our lovely world. Thank you so much for joining us live again today for another installment of Serverless Office Hours. We are streaming on the AWS Twitch channel, so welcome if you're joining us from there, on YouTube, Serverless Land, and also via LinkedIn Live. I'm Julian Wood. I'm a developer advocate for serverless here at AWS, and I'm joined by Speedy Gonzalo himself. We'll find out why. Richard Davison. Richard, welcome back to Serverless Office Hours. How are you?
I'm good, thank you. Thanks for having me again, Julian. It's been a blast since last time. I think
Yes.
we had the pleasure of. Remind me, was it? I think we did Snap Start. If memory
Yes,
serves me right.
I think it
Yes.
was Snapstart. Yes,
hmm
bad me on checking it up, but yeah. Yes. So for people who don't know you, tell us about your sort of journey. I know you're sort of based in Sweden. You've been at AWS just over 2 years. But what's been your journey to what you've been doing at the moment?
Yeah, so it's actually 2 years now already. So time flies. So I currently working in a position where I help partners to navigate the complexities and intricacies of modern applications and how to best build them and deploy them on AWS. So by modern applications, we mean serverless and container applications. So mainly helping the partners to excel with that type of technology on AWS and the AWS platform.
Well, sounds fantastic. Well, we're going to get
Yeah.
to what Richard's going to be talking about today, but just looking quickly back on the past week of serverless in the world of AWS. Last week's stream was great fun. Andy Booth from Human Graphics joined us talking about Java AI ML on Lambda. Whole lot of words in there which you think would make things really, really slow. Java, AI, machine learning models, huge amounts of storage, huge amounts of resources, but Andy has hacked everything to do with everything and has come up with a really cool solution. So Andy was super cool, and yeah, doing this amazing machine learning where he's doing demographics data, and that's all available on our Serverless Land YouTube channel along with all other Serverless Office Hours episodes. So yeah, a great back catalog of super interesting things. In terms of what's new in the world of AWS Serverless, well, actually two interesting things from DynamoDB over the past week. The top one is resource-based policies. So this is cool. This basically means that you can use DynamoDB across accounts. And there's definitely been certain chat among the industry of whether this is a good or a bad idea, because obviously you want to maintain sometimes your bounded context and things like that within a microservice. But if this unlocks being able to do migrations, being able to connect something remotely, or have microservices that can talk to some shared system, this just makes it so much easier. So that is great. And then also DynamoDB supporting private link. So yeah, this is also great for people who want to connect to DynamoDB via their on-premises workloads or via their VPCs, and they don't need to then have a net gateway or something like that. So yeah, this is super useful for DynamoDB customers. So great job. In terms of what's new in the various compute blog posts that have been coming out, the second one down, Dave Boyne has put one a week or so ago about cloud events. So cloud events is an open industry standard, and using that with Amazon Event Bridge, which has got great transformation capabilities, and basically is just messing around with some of the envelope format of the actual event, and that's really easy. The top one, Andre Stoll's actually been on Serverless Office Hours before, talking about chaos with Lambda. Well, it's actually chaos experiments with Lambda. So using the fault injection service in Lambda, super useful to be able to add some latency, add some errors and kind of things. So yeah, if you want to be testing out some how strange things would work with your Lambda-based functions, that's a great blog post. And we are live, obviously, over here, so please send us your questions and comments and say hi. I obviously need to bring up the third one down because design approaches for building serverless microservices. I have spotted that my 50 Cent, who's otherwise known as Luca Mezzalera, is on the stream. So welcome, Luca. Thanks for joining us. And Luca and Matt Diamond have actually written a great blog post on design approaches for building serverless microservices. And if you think your Lambda functions are too big or too small or right or wrong, these are some great considerations to think about. My word of it is also the pragmatic Lambda function. There's some wrong ways to do it, there's some right ways to do it, but they're all trade-offs between them. And so Luca and Matt's post is super useful. And Robert Tables, thanks for joining us again. Robert's a regular listener to Serverless Office Hours. Yeah, fault injection service is really good to feel confident in production. Love it. Some other events that are actually coming up. It is AWS Summit season, so the Amsterdam Summit is coming up is coming up soonish. There are some other summits being added to this list. I'll actually be speaking at the London Summit. I was working on my presentation today. I'm speaking with Michelle Chisholm, so that will be fantastic. If you are coming to the London Summit, please come and say hello. We'd love to meet you. Go to an AWS are partnering up for EDA Day, Event-Driven Architectures Day in London on May the 14th. We ran it about 18 months ago. It was ridiculously sold out and was fantastic. So this is installment number 2. Loads of talks are being worked on and some have been publicly announced. So yeah, really going to be useful for people wanting to build sort of event-driven architectures. Also, our friends at Fauna have a webinar on how to build serverless event-driven architectures at scale. And Fauna is a sort of a serverless database in the cloud and how they're using it with step functions. And so, yeah, the link over there takes you to the registration page. And Tanya Botu, who is our sort of top product manager for step functions, and Ben Smith, who's also our top expert on all things step functions, will be joining that webinar. So certainly take a look. So that's the future. Well, that was the past. Now sort of pivoting onto the future. Richard, a Lambda low latency runtime. Tell us about this. I know it is blazingly fast, but what was the genesis of this and why?
Yeah, that's okay. I mean, sure. That's why we're here. That's the meat, I think, of this.
We're talking about something completely different, right?
Yeah, but first of all, I want to ask you, what are you talking about at Summit? That was interesting.
I'm at the summit, the London Summit. I'm doing a slightly modified version of my serverless best practices talk. So it's 45 minutes, and we're just going to jam pack as many serverless best practices as we can, so you can get some tips and tricks. And it's going to cover Lambda and step functions and event bridge, and how you can orchestrate and choreograph and your software development life cycle, and understand some of the bits of Lambda that you can optimize. And some of it's definitely optimizing cold starts and looking at your code.
Exactly.
So you are our guru on that. So I'll probably
and on that segue, like, what is low latency runtime, or LLRT? So first of all, if I were to ask you one thing that you would that you see people are quote unquote finding challenging or seeing as a drawback with serverless applications, you might say it's cold starts, right?
Definitely. I feel as though I've been at AWS now, 4.5 years, and I feel as though cold starts just overtakes the oxygen in the room. And yes, it is a consideration, but it is, in my opinion, way overblown as a concern. Affects less than 1% of cold starts. We know that. Anything asynchronous, you shouldn't really care. There's so many things from snap start, provision, concurrency, all to do that. But saying that, obviously, there's always work to do to optimize cold starts, and specifically when you are running synchronous APIs. Certainly, it is something to look at, and we all want to do the best to reduce it where we can.
Yeah, exactly. And to your point, I mean, I think the whole conversation about cold starts and the cold start quote unquote problem, it's not really that much of a problem, right? Because when you take a look at production metrics, you can see exactly what you say. It's about 1%, maybe, to many cases even less than so. So cold starts, they typically occur during the development of your serverless functions. When you do a new deployment, you invoke it, you can see it takes some time. However, right, optimizing for cold start is a good thing, because the more you can optimize for cold starts, you're likely to have less cold starts. So the faster we can make any cold start means that we will have less cold start overall. And that's the reason why, is because whenever your Lambda function is busy and get two invokes at the same time and hasn't had two at the same time before, it has to provision an additional execution environment. But as soon as it's done so and has two already ready to go, it won't happen again, right? But if you can optimize for that, so every optimization that we can do will be beneficial from both a user experience perspective, developer experience perspective, and also a cost perspective. So in its current landscape, we basically have the execution model of supporting a whole heap of languages, from Java to Python to Node.js. You can even run custom runtimes on there. We have .NET. We have basically, you name it, we can support it, right? Especially since you can build your own. But my approach here to try to tackle this problem is that rather than taking like an existing general purpose programming language and execution model that are typically built for serverful or traditional server environments, I try to take like a bit different approach to looking at it from the other way around. So taking a look at the resource constrained environment that we have inside of AWS Lambda, where we want to keep our resources as low as possible, meaning the memory. We want to keep the memory as low as possible from a cost perspective, right? With those premises, how can I build something that are built for that purpose? Say 128 megabytes of memory and the corresponding allocated CPU or vCPU that represents, right? So less resources available and an execution model and a programming language. What would fit that best, right? The best answer is really go native, build something in C++ or C or Rust or something like that. But in reality, customers are not going to rebuild everything in Rust because it's rather complex. It has a steep learning curve. It me myself that I'm pretty well versed with Rust sometimes find it less productive than other environments. And there's also a benefit of having something that you call an interpreted approach, meaning that you execute something straight from its source code. Think Python, think Node.js running JavaScript, etc. So with those premises, what can I do, right? So I started taking a look at the problem from this angle, and I came up with JavaScript is a really good programming language, right? It has a very active community, has a lot of support. It's actually one of the most popular ways of running Lambda functions. Like Node.js is one of the most popular runtimes. So with those premises, how can I work around with that? And the good thing also about JavaScript is that it has had a lot of innovation in the recent years. So there's not only Node, there's also Deno and Bun and a whole heap of other runtimes and engines that exist that is able to execute JavaScript. You can even run JavaScript in Java, which is quite funny. People sometimes confuse them to be the same thing, but you can actually run JavaScript inside of Java in that runtime, right? But there's also a lot of really lightweight runtimes and lightweight engines. So there's a difference between an engine and a runtime. So what I did with this project is that I took a JavaScript engine, something that is able to execute JavaScript, but it has basically no APIs. So it has no console, no file system, no networking, nothing like that. But it's able to execute JavaScript, and it's very, very lightweight. And this project is called QuickJS. So it's basically a huge C file, 50,000 lines of C, but it's very, very lightweight. So the whole engine itself comes in under 1 megabyte. So in comparison with what's running inside of Node.js and Deno on Bun, it's up to 20, 30, 40 megabytes. So imagine being 40 times less complex in a sense. Obviously, that has some drawbacks, but we'll talk about that later. But that means it's a very lightweight package. So can I take that and build some APIs on top of it and also have a different approach here? I'm going to use Rust because Rust can compile to native or actually compiles the native code, meaning that it will be very, very fast and will have minimal cold start. So combining the two technologies, Rust with an APIs and a lightweight JavaScript engine that exposes those APIs. And at the same time, try to make it compatible or partially compatible at least with the Node.js specification, meaning that it should be as low effort as possible of porting your existing Node.js applications and make them run on Lambda with minimal cold starts. So let me share my screen here.
Yeah, certainly. I mean, just to pick up on some of the threads in there, I like the sort of focus actually on cost, because a lot of buzz has been happening all about, well, this is super blazingly fast, but as we know with Lambda, cost is directly corollary to speed. So anything that you pay per gigabyte seconds and the amount of memory configured, so less memory, less execution time is going to be lower cost. And
yeah.
I know we have customers that are running Lambda at absolutely ridiculous scale. They're not necessarily complaining about costs necessarily, but if you can shave milliseconds off of their runtimes at the scale they're running, that's significant dollars that goes back into the company to do other kind of things.
Exactly, and it's not only just saving. We talked about cold starts, right? So it's not only just saving of the cold starts, which in fact can be up to an order of magnitude, and that is like 10 times faster, and even more so. We will see it later in the demo here, but it's also for the warm starts.
Yeah.
And the reason for this is, again, this simpler approach, a simpler engine, meaning that it actually works better if we have low resources. So if you think about it, it's kind of obvious, really, because Node.js, Bun, Dino, all of those runtimes, they're fundamental components, they're engines. They come from web browsers, and a web browser is not purposely built to run. The technology is not purposely built to run in an ephemeral environment. Something that starts quickly and gets discarded quickly. So they're built to be run in web browsers. So it doesn't really matter if your Chrome browser starts in 500 milliseconds or 200 milliseconds. Nobody's going to care, right? Because you spend hours and hours in there, and it will optimize over time. So these all rely on a technology called JIT, or just-in-time compilation. So meaning that every time a JavaScript function is called inside of the engine, it will be analyzed by a profiler, and the profiler will generate machine code that will then get executed. This is great for that long-running task and for a sustained workload when you do hundreds of thousands of iterations or even millions of iterations, or browsing the web for hours, right? But inside of Lambda, with that low memory footprint, with that low memory resource, we can't really rely too much on that fantastic piece of technology, because it requires a lot of memory. And we can use that precious memory and the precious compute required to do this just-in-time compilation to actually do execution instead. So this means that we conserve a bit of that execution time for Lambda function in a time. So rather than profiling and try to find an optimized way of executing your JavaScript function, you can actually start executing it right away. It doesn't really matter if it's if it's slower over time, because we're not really using that over time. We're using it for a short term.
You're refreshing the runtime, very regularly. So it's all being refreshed as very often. Yeah.
Exactly, and the environment itself, first you have a cold start when a new execution environment is provisioned. Then it lives for X amount of minutes, and that can be anything from like 5 minutes up to 1 hour or something like that. It's really not defined. It depends on a lot of factors, but it's still with few resources, it's not enough that it will give you the same level of benefit as a sustained constant or a traditional running application inside of a server will do, right?
Yeah.
So this has some drawbacks. The drawbacks is that if you do something for millions of iterations, hundreds of thousands of iterations, you do some calculation, compute heavy things in JavaScript, you do hash calculation, Monte Carlo simulation, your performance will suffer using LLRT. You will have a better experience using Node. But the majority of times, Lambda is maybe not the best way of doing that type of work anyways, right? And if you're not doing that, if you're doing integrations with AWS SDK, or if you're doing some sort of data transformation, data enrichment, that glue code, to communicate between different services or talk to other downstream APIs, you will have a positive user experience and an order of magnitude faster cold start for most use cases, and two times lower cost for warm executions as well. And we will see this shortly in a demo as well.
Yeah. And I like that focus actually on the warm start performance, because as I said earlier, the oxygen seems to be taking out the room on the cold starts. But
yeah,
what I do like about people who are investigating cold starts is that makes them sort of wake up and find out and make all of their code more efficient, which is also going to impact their warm starts. And so although we talk about cold starts needing some work and being able to reduce that, some of that work that people are doing to reduce their cold starts definitely impacts the warm starts, and that's actually probably the better story about being more efficient with your code. And so LLRT is taking that sort of to the extreme by optimizing it as much as you can. And I like even the bigger concept of sort of starting from scratch. I love that idea. Serverless is all about building on top of primitives, well, this is starting from a primitive that's built for serverless and only adding the things you need rather than being as general purposes, maybe needing everything.
Yeah, and then exactly then of course what's the catch, right? So this has to be some sort of caveat with this approach. And yes, like I mentioned, one of the catches is if you do compute heavy things in JavaScript, you do say you calculate the hash value, but you're not using the native APIs that I provide. You do it inside of actual JavaScript manually, so to speak, right? That will have a huge benefit of running through a just-in-time compiler with this optimization pass that the profiler runs and starts getting better and better over all of these iterations. But again, if you're not doing that's you're fine. The other caveat is, since this is a lighter engine and a lighter approach, I can't support every Node.js API. Node.js has been around for like 15 years. It's a huge API, and their focus has been on backwards compatibility as well, right? So they have a huge API that works on, I don't know how many OSs and devices. It's 10s, 20, 50, I don't know. It's a lot of, all Linux, all Windows, all Macs, everything works with Node.js. Browsers, whatever, right? It's fantastic. So this is it's not meant to compete with that platform. Neither is not meant to compete with Bun or Dino, but it's meant to be as a complement, as an alternative when you're doing API integration, when you're talking with AWS SDK, which in fact is included and optimized specifically for LLRT. We'll see this also later in the demo, but it takes a different approach. So obviously the trade-off here is, can I keep it lighter? And this is by design. And the tricky part is to determine what APIs should I support and what APIs should I not, right? Because every time I implement a new API or the team implements a new API, it comes with a cost. It will add slightly to the cold start. So we want to keep it as light as possible. So right now, the entire LLRT binary, when deployed on AWS Lambda, the entire runtime with all the APIs and the SDKs that we support are less than 3 megabytes. In comparison, Node.js itself without the SDK is like 80 megabytes. So you can just see, by looking at the size of the binary itself, is a huge difference. And this again, what you get in return is that really fast startup time and that really low cold start, but also that sustained, constant, warm performance that is actually lower with constrained resource environments. And then someone might ask, but what if I crank the memory up, right? I give Node.js and Ordino or Bun the memory it deserves. I give it 2 gigabytes. Is it still faster? The answer is actually it's about the same speed, because I also get more resources to execute with LLRT. But now if you do like API calls, you're going to spend a lot of those precious gigabytes in CPU by just waiting for the waiting for the latency of the API call, which can be 10, 20 milliseconds, depending on what you're talking to, right? So now you're just wasting CPU time. So you're not going to see any cost benefit. And I tried this, I try adding, back and forth, seeing what would happen. And I haven't found a single way where Node is faster than LLRT with all the tricks in the book, right? And there's a lot of tricks you can do. And I know most of them. I didn't know about the environment variable thing until recently, but that's also something. I tried every trick in the book. And since I know that I'm building for Lambda, and it's an environment that I'm very, very familiar with, I can incorporate all those tricks inside of the runtime so the customer doesn't have to know about it. And the users of LLRT, when deploying on Lambda, doesn't have to know about all these tricks. A good example of this is when you import an AWS SDK client inside of LLRT, what happens in the background is that it initializes the connection to that service that you're about to call, since you imported. And since we're initializing the connection outside of your handler, it gets better performance, because Lambda gets a bit more, get a bit of a boost when it's initializing. So we utilize this boost, and the customer doesn't have to do anything, right? So that saves like 20, 30, 50 milliseconds even, because it takes a lot of CPU resources to initialize a TLS connection that is like a secure SSL connection. So things like that I can incorporate, and I can take the AWS SDK, convert it into bytecode for the engine. That is like a parsed format that the engine first reads through your source code, converts it into bytecode, and execute that. I can do that at compile time. So I save an additional milliseconds. And I do a lot of these small tricks that you don't see, and doesn't make any difference to how you write your JavaScript application or how your source code is defined. In fact, you can even run, in the demo we'll see this, you can take the exact same code, just switch runtime to LLRT, and you get 10 15 time cold start improvement and 2x warm start improvement by not changing a single line of code. And this is like a DynamoDB call, which I think is really showcases the potential here.
Excellent. Well, I mean, we sort of teasing a demo. Maybe we should
Yeah.
look at something. Or I think,
why not?
Yeah,
Why
people
not?
are getting itchy to go. Show me the money. Show me the money.
Yeah, exactly. Enough talking, Rich. Show us the stuff, right? So let me share my screen. So first,
also, yeah, while you bring up your screen, one of the interesting things, and I think it was Bill Roos, who used to work at AWS, met him at reInvent. He was super cool about discovering that environment variables actually add a little bit of latency, and that's because it's using KMS to decrypt the environment variables, and so it takes some time. So I love how the community finds these little things that work with Lambda. And just so you know, internally, one of the things that does slightly grate me is when people in the industry say, oh, well, of course, Lambda is not going to be as fast as possible because, we charge money by the millisecond. And so we don't have an investment in making things fast because we lose money. But I mean, I tell you that the opposite is entirely true. The amount of time and effort that goes into shaving, milliseconds, nanoseconds off SDK calls, internal processes and services to make Lambda literally as fast as possible, is a massive driver for what Lambda does. And internally, we see emails coming through where they'll shave off even 1% CPU usage for some. Maybe it's going to be an observability process. And you think 1% performance, never mind for customers, but across our trillions of invokes a month, that is a massive resource and performance boost for everybody. So so please never think Lambda's deliberately making anything slow to make money.
No, yeah. And I think this is like a really good observation also, Julian, before we dive into the feature highlights here in demo, that we're actually incentivized the other way around. So we're not incentivized of making it slower because we make money of Lambda. We're incentivized of making it faster because customers save money on Lambda. That might sound like counterintuitive, but it actually makes a lot of sense because we see like if we provide a great user experience with Lambda, and if customers can run really, really cost-efficient code, they save money by switching to Lambda, they're likely to invest in other AWS products or use a database or use something else or move their workloads over to AWS because the experience is good. And we care about our customers and the user experience and also the developer experience. So if you can make it faster, it's a win-win situation. Our customers get happy, the user experience get better, they get lower cost, and they're likely to reinvest and doing innovation across their other places of their stack.
Yeah, Robert Tables hits the nail on the head. I don't think we're hiding anything by saying if you offer a good customer experience, people are going to use more of what you're doing. So that's what keeps.
Someone said here also, Robert in the comments said, like if you smart spending. If you save money on like compute and on one service, you can invest in other products, which also needs somewhere to run. And if you have a great experience on serverless and on Lambda, why not continue with that, right? So it's a win-win. So cool. Let's dive into some of the feature highlights. I've addressed most of these already, but just summarize here. We see, with LLRT, we see negligible call start. So most of the calls will actually happen in less than 100 milliseconds inside of AWS Lambda, right? LLRT supports JavaScript or ECMAScript 2020. It's not the latest standard. I'm working on an update to 2023, which is the latest standard. Technically, it's possible, but working on that, so it will come. And it supports a lot of Node.js APIs. Obviously, not all of them, but basically the most you need. File system, even HTTP sockets, fetch. So the goal here is to have as low as migration effort from Node.js as possible. It comes included with the most popular AWS SDKs. Not all of them, but the most popular ones. And you can always bundle your own AWS SDKs if the ones that I bundle and embed inside of the runtime it doesn't fit your need. And it comes with, I think, the most interesting part here, cost and performance benefits. So we see those lower cold start and even lower sustained warm start and lower costs on those as well. Right. So under the hood, we talked about this as well, using QuickJS. It uses an asynchronous runtime for Rust. It's built in Rust using that's named Tok.io, and the APIs that conform to the Node specification, they're all implemented in Rust. In contrary, in Node, most of the APIs are actually implemented in JavaScript. So it's heavily dependent on JavaScript, whereas LLRT tried to make as much as possible inside of Rust for that added performance benefit and the lightweight of the application. And it's about 3 megabytes, including the AWS SDK. Now, I think it's time for a demo. Or do you have a question, Julian?
Well, I just have one. When you rebuild, when you're rewriting a whole bunch of stuff in Rust, I mean, is that a complex job to? Are you literally looking through the API spec for Node.js and re-implementing the code in Rust? I'm sure it wasn't as easy as just taking a Gen AI model and going, "Dear Rust, dear Node.js, please convert over to Rust."
No, it's not. Yeah, I wish almost. Yeah, but it's not that. It's not extremely complicated. It's what's most complicated is, of course, the low-level stuff like file system and networking and things like that, and also the event loop. But I also rely on dependencies that makes this really simple. There's an excellent dependency for Rust that is called rQuickJS. There's Rust bindings for the QuickJS engine that abstracts away a lot of the complexity. Then I simply, which is not, it's not a simple task, but I have to convert the APIs into Rust specification. But the create, which is the name for dependency in Rust, matters. So shout out to the team behind that, and there's a guy from SurrealDB who's the mind behind that. I'm having a conversation with him, and also submitted a few PRs to that project also as part of this. So yeah, it's complicated, but it's still it's manageable, right? So that's exactly what I do. I look at the node specification, I see how it works, and I implement the same thing with LLRT, and I pick the ones I think are most relevant for our customers and that customers want, right? So I think enough teasing, right? Now it's time to go into, I hope that my screen is visible. Let me bring up, you can see my browser, hopefully. Let me zoom in a bit. Is this visible?
Yes, that is visible. Or maybe one more for the people.
One more for the guys with glasses. I have glasses myself, so
me too.
I just hide them. I've abstracted them away behind lenses. So okay, let's start with going back and let's see. I'm changing the runtime settings here to Node.js 20, which is the latest one, just to see how this code would perform using the regular Node.js runtime. So if you go through the code real quick here, this is a very simple example, but it kind of showcases, because it's kind of a real world example. I'm putting some data onto DynamoDB, and I'm returning the status of 200 and a body of OK. So what the data I put on DynamoDB is actually the event that gets passed into Lambda. So I took the event here, I convert it into JSON or JSON stringify it and put it inside of an object called content together with a randomized ID in here, right? That's all I'm doing. It might sound trivial, but it's actually a lot of things happening in here. So let's see how this would perform using Node.js regular runtime. And the event that we're going to, it's just a simple, demo hello JSON event. So let's test it with Node.js runtime. So we're executing, and I'm using.
So also because you've changed the runtime configuration, this is a whole new Lambda function in effect.
Yes, this is a cold start.
Starting from scratch again, yeah.
Exactly, we're starting from scratch. We can see also that we started from scratch because we had this init duration here. So if we have a cold start, we will see this init duration here, the value that I'm highlighting. So we have an init duration of 354 milliseconds, and we have a duration of 970 milliseconds. And the total duration is actually these two values combined. So we have the duration, the code that is happening, or the measurement, I should say, that is happening inside of your handler. And this is outside your handler while it's being initialized. So we combine them, say 1.2 seconds, right? 1,200 milliseconds, something like that. we have 128 megabytes of memory configured, so the lowest possible value for Lambda. But we used already, for the simple example, we used 88 megabytes. So pretty, we're not having loads of memory over.
Yeah.
But let's now switch to LLRT. And I prepared this demo by putting the LLRT binary and rename it Bootstrap here. You can download LLRT from our GitHub. We will have links in the show notes and also at the end of the presentation here. So I've simply downloaded the zip. I'm running an ARM function here. So I downloaded the ARM build of LLRT. It's actually named Bootstrap already. And I just put it together with my source code here. That's all I did. And then I go down here to runtime settings. I edit them and I select Amazon Linux 2023 OS only runtime for Rust, Go, custom, etc. That's all I'm going to do. I'm going to hit save. I'm keeping on ARM. I get slightly better performance on ARM and slightly lower cost. So let's go back to test. So I didn't touch the code. I just leave the code as it is. No changes to the code. I go to the test tab. Again, this will be a cold start since we changed the runtime settings. I'm going to test. You can see this was really fast. Now we have an init duration of 35 milliseconds and a duration of 35 milliseconds. And in total, we have 71. So remember, 1,200 almost in total versus 71. So it's quite a dramatic increase in performance here. And I have the same code. I do exactly the same thing with the code. I'm putting the same event on DynamoDB and have a max memory usage of only 21 megabytes. So if memory serves right, it was about 88 megabytes for Node.js. So it's orders of magnitude faster. Let me see, 1,200 divided by 71, 16, almost 17 times improvement here. So not 1.7, but 17x improvement running the same code. Yeah, and doing this for if I continue here for warm start, we can see 18, 17, 28, 11, etc. Really, really, really low, right? For these warm starts as well. The biggest number
and
is
this is not
like,
just a hello world. This is not just turning something to an API. This is actually writing the event to DynamoDB as well. So there's always going to be latency over a network to write to DynamoDB. I know it's fast, but yeah.
Yeah, you can see here it's about
it's a proper Lambda function in a way. Yeah.
Proper Lambda function. It's a proper use case. We're getting maximum about 20, 25. I think I saw 50 for one, but that was when the connection was not cached. Now the connection is established. We can see really low, about the same, between say 7, 8 to up to 25. Let's say that. Also go back here now. See the warm start performance of Node.js just to get a comparison. Node.js 20. I go back. This will now be a cold start again. So there we go. Go back to testing.
Thanks, Frag0_ for joining us via Twitch. Kapow, we're all talking the really fast stuff. So this is cool to see.
Yeah, and now we see again, it's about the same. We got 1,200 again, and consumed 88 for the cold start. So let's now see warm start. You can see the first warm start evoke. I got like 50 on LLRT. I got 400 here, and 61. 26, 62, 50, 37, 45. You can see we got about 25, something like that. The reason here why it jumped so much up and down is because of the just-in-time compiler. So we'll talk about that.
And also that first warm start was still 400 milliseconds because that's creating the initial connection to DynamoDB, which you're optimizing in your runtime by transparently just running that in the unit.
Exactly. All right. So there's a less consistency here. So if we go back and see, what if I run this for a very long time? If I run this for, let's go back to the presentation here. So if I run this for 32,000 invocations with the same code, right? And I see here, let's bring out this number. See, we see LLRT with 32K invocations, and this is. We see cold start on the first, on the second row here, and we have warm start on the second. We can see the P99, meaning that 99% of all invokes are below this number. We see the maximum we got here was 84 milliseconds, and for a cold start, and the P99 for a warm start was 34. And similarly, the fastest possible we got for a warm start was 5, and 50 for a cold start with LLRT. So 50 milliseconds. compare this with Node.js, this is 18. It's not 20. It's slightly faster, but not dramatically. I haven't updated this. I should probably do. But in comparison, we see here we got 1,300 for P99 and 1,100. So it's a huge difference. You can see it's a 23 times difference between the best case for a cold start for LLRT and Node.js. And for worst case, the worst possible P99, we have a 15-time improvement. And also notice here the number of cold starts that we see. Since it's so fast, like I talked about in the beginning of this call, we're also much more likely to hit the cold start. In fact, it's 5 times more likely to hit a cold start when running Node.js with the same code. And also, we saw this fluctuation. So if you take the slowest or the fastest possible time for the warm start here and the slowest possible time for the warm start, there's a fluctuation of 158. That's the span of which the duration differs. And take the same, look at the same number here in LLRT. It's only 29, so it's much more consistent. You get this consistent performance. This will correspond to great not only savings but also, of course, user experience. So if we go back here, we can see that the total duration of everything executed, if I sum up these 32,000 invocations for Node.js, was 27 minutes and 40 seconds. So counting all the times of 32,000 invocations. But with LLRT, it was just 7 minutes. So we have a cost saving of 2.9x and a time saving of 3.7x. And the reason why these two numbers differ is that you're being charged a bit differently depending if you use a customer runtime or if you use a provider runtime. So it's actually the difference between build duration and total duration. But regardless, we see almost a 3x cost saving using the exact same code.
And also with the OS only custom runtime, you are paying for init as well. So
yep.
So you're paying that little bit extra, but because it's so much faster, you're still saving a bunch of money.
Yeah, you are, exactly. And you get it. There's no surprises here. You get this consistent performance. Only a difference between in 29 milliseconds, right? So I think we can end screen share here.
Wow, I mean, fantastic. What I like about that is that the demo is actually so simple, where you're not even having to redeploy or change any of your code. You're just switching between the runtimes in the console, and it's over there. And I mean, the bootstrap, you just need to add the bootstrap file into your function. You don't need anything else.
No, exactly. That's it. And of course, I mean, this was a prepared demo, so I know that the APIs that are in here are supported. I'm using the AWS SDK. You can check out the LLRT repo that will be in the show notes. That has a list of all the supported SDKs. But the supported SDKs are supported in fully, right? So you can use all of the calls and all the things that we saw. DynamoDB, S3, we have KMS. I think we have a lot of SDK clients that are embedded, and you can always ship your own as well. We have the primitives that support it that will work on LLRT. So
So if people are thinking, obviously, scratching their heads, thinking this is fantastic, save money, be faster, but then they don't know whether their API is supported, what kind of things can they check? What would be something that wouldn't be supported that you can straight away say, heading up the wrong tree doing this? Obviously, you can test your functions and see if it works, but just for people who are thinking about that, what should their thought process be?
Yeah, that's a very good question. I'm glad you asked it. So the first thing that you would do is uploading your code and testing it with LLRT is not the smoothest user experience, right? Because you need to do a new deployment every time, and then you find an error, you have to find where does it crash, etc. You can actually run it locally on your machine. So it supports running on ARM Max or Intel Max, or Linux machines, both for ARM and x86 as well. There's no Windows support unless you use the, what's it called, the
WSL, Windows Subsystem.
Yeah, exactly. Yeah, then you can run it on Windows as well. So that would be the simplest thing. There's also
how do you actually run it locally? Is that
you download the version for your OS? There's a Mac build on the release page on the GitHub, so you can just
Okay, as just a binary. So do you just literally run the binary? Okay, so it's not even
binary,
so it's not even having to use a Docker image with some pretend of Lambda, or SAM has a local invoke, AWS SAM is local invoke, which is all sort of useful. You don't even need that. You're just literally running a binary.
Yeah, exactly. And LLRT will actually detect if it's running inside of a Lambda environment or not. So it will automatically have the Lambda API handler and all of that built in. So it will detect if it's running inside of Lambda, it will perform certain things. And there's actually a special build for Lambda that is a bit more optimized. And the one that for local development is optimized for that environment, but also it has a built-in test runner. Right, so it supports running unit tests with expect and Jest-like API. Not, of course, everything from Jest is supported, but you can check out the test folder in the repository, and you see how our tests are done. You can do the same thing, just importing the APIs, running it locally. Just point to an index file, and you would see what works. What would not work right now is streams. So web streams or Node.js streams are not supported. We have a fallback, so you can use streams inside of JavaScript. But remember, as I told before, streams is an API that gets called thousands or hundreds of thousands of times, for basically every byte that flows through the stream.
There's an optimization built in.
Yeah, there's an optimization opportunity here, and we're working on it to converting that into native code, right? So building the streams API in Rust, and that's like a huge endeavor, but we're getting there. Where that's the ambition to getting this done. And speaking of compatibility, we also aim to have something called Winter CG compliance. And Winter CG is a working group that tries to have a common set of APIs that are supported cross runtimes. So regardless if you're running like on Lambda or anywhere else, or in any other engine, I should say, so Dino, Bun, Node, what have you, LLRT, you should be able to execute the same code and have the same set of expectations. And that's called Winter CG. It's like a work in progress, but there's also a working group behind it. So there's a lot of companies behind that. So that's also something that we target for LLRT, to have it Winter CG compliant.
Web Interoperable Runtimes Community Group.
Yeah.
There we go.
That's a mouthful right there.
It is.
Right? So.
Winter CG sounds much better.
Yeah, that's why people just use that. Exactly, Winter CG. So check it out. It has like an API. There's even I think there was someone had like a comparison between all the runtimes and which Winter CG's API that were implemented and supported and whatnot. So we can see if we can find links to that as well. But the simple answer to get started is just to test, and test on your local machine first is way easier. We're also working on providing typing. So if you use TypeScript, that will make it easier for you to see, what's supported inside of the engine. And there's also check out the demos. I know that people say, okay, yeah, this is a demo in favor of LLRT because it uses the AWS SDK, DynamoDB. I don't use that. Can you do something more cool? Yeah, that we have a React to-do list that is also running. Everybody does to-do lists in React, but it gives you a good comparison where we actually store the to-dos inside of DynamoDB. It's server-side rendered. It runs inside of LLRT. And in comparison, we compare that with Node, and it's still massively more performant. And React is there's a lot of JavaScript in there. It's like, I don't know how many thousands of lines, but it's a lot of JavaScript, and it's still much more consistent performance, and it's also lower latency than it is with Node. So still, rather heavy JavaScript application will still benefit, right? But of course, there is a limit. How much JavaScript can I shove in there when I will have an edge of using something else? So that's the simplest answer would be to just start with LLRT, see where you hit a corner. If you hit a corner, you can always switch back to Node because we have the same specification of the APIs. So the whole goal behind this is to not have your efforts wasted. So I don't want people to they invest a ton of time and try to make it compatible with LLRT, and then they run into a corner. Oh no, this is not supported. Then you can just switch back to Node because they follow the same specification. So that no effort wasted, And you can mix and match, right? You can have one Lambda function using LLRT, another one using Node, even across versions, right? You can do A/B testing and see, does it work for you? Will it crash? How does it perform over time? And I do also want to highlight that this is still an experimental runtime. It's not an official, it's not an official AWS product. It's still something that is quite early. It's like a beta release right now. We're still finding bugs and issues, and I really appreciate that everybody taking the time to test it out. The best thing you can do is just write an issue, try to make it reproducible in an easy manner that will help us, and also just raise feature requests. I really want this API. I really need this AWS SDK support. Hey, Richard and the team, please help me, and we will do our best to try, to support that. We're working on streams. We're working on cryptography to adding, to allow Lambda to be used as an API gateway authorizer, or LLRT to be used as an authorizer, which is a fantastic use case since it's sits at the edge of most APIs. And it needs to be fast because it adds latency on everything. So there's the best thing you can do is test it out and provide feedback. And I appreciate all that feedback that's been coming through. It's been fantastic so far and really encouraging.
Keep it up. Well, actually, based on what you said, Graham Campbell, thanks for joining us, Graham. When will this be available for Lambda at Edge? And that was, back to your previous comment, this isn't an official runtime. We're in beta and testing at the moment, but, the Lambda team is certainly looking at this and going, what can we take from this, usage of this and uptake of this and interest in this will certainly drive, product enhancements within Lambda as well.
Yeah,
specifically for Lambda at Edge, Lambda at Edge does only support Node.js. So as this is a custom runtime, that's
and Python, right? Yeah,
and Python, yes, Python, and so unfortunately, when is we don't know yet, but
no, we don't know.
We shall see.
We'll see what happens, right? Again, we're trying to make it as best as possible. So the more feedback that we get, and the more customers are using it. I mean, it will only help, right? It only help people pushing it forward. And of course, there's also a slight benefit of having it as a provided runtime. We can we can cache it better. We can have even lower latency because it can be live closer to the workers than custom runtimes. But that's also one of the reasons why we make it really lightweight, because it needs to be shipped together with your code, right? So it's important to consider these things, to look at also not only the time you see inside of Lambda, as you saw in my demo, but look at the end-to-end latency, actually, flowing through API gateway or doing an invoke from your local machine. How long does that take? Because that will affect things like code size, size of your runtime, all of that. So measure and see is the best advice I have. Cool. And also tweak the memory settings or use LLRT and tweak it down, right? That's the best thing you can do right now.
I can see the feature requests of 128 meg for Lambda. That's too much. We need to have less memory, please, because all of my LLRT runtimes are shorter. Yeah. So I just wanted to quickly cover off some of the deployment options as well. Obviously, it runs on a custom runtime, but I understand that there are two different ways you can add the bootstrap to the custom runtime. One is just including the bootstrap binary along with your JavaScript code, which you showed in the demo. But the other is just adding a Lambda layer. So you can, if you want to not upload your bootstrap for every single function, but you want to just maybe maintain that centrally, that's a possibility. So you can also use a Lambda layer to just, add that to your Lambda function, and your LLRT runtime is just there.
Yeah, you can just, what you can do is if you go to the GitHub repository, you go to the downloads page, you click on the latest release, and you download LLRT Lambda, say ARM, then you can upload that straight away to a layer because it already contains the file named Bootstrap. And Lambda will automatically detect that your layer has a file named Bootstrap and you're running custom runtime. I selected that as a runtime. And it will just point that as an entry point. It will use that Bootstrap file as an entry point, and you're golden. You're good to go. So that's maybe the simplest approach if you want to test it like right now in 5 minutes. That's something you can do.
And also, of course, you can package LLRT in a container image if you're building your Lambda functions with container images. Some people may think, oh, that's a bit strange because container images is all about large package sizes. But I know many customers who run, have huge big files that they want to process, or they want to use huge amounts of memory. I don't think these things are necessarily orthogonal. Maybe you've got a big machine learning model that you want to use or copy elsewhere. I don't know, do something like that. But you can have big container images and still use the performance of the LLRT runtime within a container image. And that's also just looking on the GitHub repo. That's also super easy to add it. It's just a few lines within your Docker file and you're ready to go.
Yeah. Exactly. You can, again, add it to the Docker file. Again, I encourage using a very lightweight Docker file. So use something like Alpine or BusyBox even as a base image. Since LLRT contains everything you need, you're good to go. There's a SAM demo there.
CDK as well.
CDK demo, SAM with container and with SIT that you can just run. You can have a local invoke there as well, and you should be good to go. So
then also, one of the things that people are using their node modules for their dependencies, one of the recommendations I see is obviously not to deploy your node modules without bundling, minification, and tree shaking, because then you are just adding bloat into your package. So there are some, using different bundlers from ESBuild to Webpack. If you are, and Rollup as well, So you are. You need to do some work if you're going to be adding more dependencies, because the point of this is to be lean and mean. The more bloat you add to your Lambda function, you're sort of going in the wrong direction.
Yeah, exactly. And also, well, the reasons is the LLRT doesn't support the Node.js module resolution, which is a whole beast in itself, like how it resolves modules. It can import node modules for sure, but you have to be explicit about the path, so it doesn't use the same mechanism as Node. You can't just put all the node modules in there and expect it to work. They won't work because all the APIs are not supported, but it also adds bloat. It's kind of counterintuitive. I also get a common question here. We just, why don't it run TypeScript, or can it run TypeScript? Technically it can. It's not that complicated because there are already TypeScript transpilers built for Rust. So I can add a dependency, transpile the code, and make it run TypeScript. But I don't really want to, because that adds time again to this precious cold start and to the precious init time. So we rather see it that you do it once when you deploy your code, and then get the benefit of executing already transpiled code. Otherwise, you're paying a performance penalty for every cold start. So it's again, following the best practices of moving as much work as possible away from the actual init and invokes inside of Lambda and doing it early. That is the same thing, building a cache or something. If you can do it ahead of time, if you can do it at compile time, that's all the better.
And just quickly looking back at some of your comments, really appreciate they all coming in. Velson4 said, this was earlier on, we were talking about cold starts. Snap start with Java for business logic and some of your commands, and then LLRT JavaScript for queries. Seems really good.
Just there you go.
Just different ways you can use that as well.
Mix and match.
Tech Hunter Kale said, and this is slightly differently, but I wanted to cover this. Just joined. I have a Lambda. Welcome. Thanks for coming via Twitch. I have a Lambda function on TypeScript. I need to start a step functions execution from an API gateway call. The Lambda needs to respond under 3 seconds. How we do this? Seems like the whole execution times out due to cold start. Any caveat for this? If you are, I would say, if you are having more than 3 seconds cold start with a TypeScript function, you've got a lot of stuff in that TypeScript function. You really there would be ways certainly to respond under 3 seconds. I would look at what your TypeScript is doing. If there's not, if you've got using the modular SDK, for example, for JavaScript version 3, remove everything you don't need. If not, look at minifying, tree bundling, tree shaking, all of that kind of thing to get your package size down. But this is very possible. Of course, I mean, it's 100% possible, even on David's, on Richard's, got your names wrong around. Even on Richard's demo, we were seeing 1.2 second Lambda function runs go into DynamoDB. So, there's proof that can happen.
Definitely possible. Yeah. So my three hot takes, like Julian said, be mindful of the dependencies, do as much as work as possible early. So minifying, tree shaking, bundling, upload a single JavaScript file. Yeah. And finally, do as much work as possible outside of the handler. Can you do work before your event comes in? Meaning that, do you have any work that you can do that is not dependent on what's inside of the event? So, creating new instances of the API clients, initializing connections, even doing a fake call with some mock data to the SDK.
Just to initialize the connection, yeah. And Robert Table says, avoid table scans if you're talking to DynamoDB. Literally in 10 seconds, Ryan Cormack. Hello, Ryan. How are you? LLRT and the Lambda web adapter. Is that possible to work together yet?
Yeah, sure. Wouldn't make so much sense, because then you will add, the web adapter itself would be more heavy than LLRT. So we'll just add additional binary. And it's more meant for web adapters, more meant for having a server application or a server framework, and that don't talk directly with Lambda. So it wouldn't make much sense.
Cool. Quickly, seconds to go. Building serverless applications with Terraform. Anton and Davison are on next week. Same time, same place. We're, in fact, slightly different time because American clocks have changed again. So if you're in Europe or outside the US, it will be an hour later. But Richard, thanks so much for joining us on Serverless Office Hours. Amazing work. Love fast stuff in Lambda. Thank you very much. And everybody, see you next week.